there's so he just asked about in section 3.6, which is another area which probably should work a little bit in. And in 3.6, I've found one good word problem I might want to look at, but he just asked me about 31, which is a decent question. 31 is this function. Its g of x is e to the 2x arc sine of x. And it's just a derivative question. Please do a derivative is all this is. Please do a derivative. So let's do it. What would you say to me? Please say something to me. Okay. First thing I think I might have heard was it's definitely a product rule. You got two functions there. One's an e function, an exponential function, and the other one's an arc sine function. They're multiplied together. We definitely have to do a product rule. When we do a product rule, here we go. I'm going to do the derivative of the first. The derivative of this first e function. So what is the derivative of any e function?
E.
Just himself. But we need to do the derivative of the little 2x. That's called doing the chain rule. Spits out a 2 right there. Multiplied 2. And then I write down the second function. Plus, I write down the first function. And now I have to do the derivative of the arc sine, which I hope I have. I just would like to have that memorized. The derivative of arc sine. Now, all right, it is 1 over the square root of 1 minus that angle x squared. If it was more than just whatever that x is, whatever that angle is, it's not an angle by the way. Whatever that input is, we would square it. If it was a 5x, we would square it. It would be 25x squared, right? So that's it. We did it. Yes, Carlos.
When you did the product rule,
Yep.
why is there a 2 in for arc sine?
Why is there 2? Because I took the derivative of him. And the derivative of the e function is himself, but the chain rule says you're not finished until you do the derivative of the 2x, which is a 2. So this 2 is the derivative of this 2x. It's the chain rule working on this.
Oh, and why is it 1 over the square root of 1 minus x squared? I thought it was u prime over that.
Okay, and what is u prime? It is u prime, and u prime would be the derivative of this x, which would be the 1.
Oh, or the one that's directly in front of the trig measure function. Oh, and that's giving 1 over the square root of 1 minus, and then that x being squared. Oh, right, I see.
Yes?
Would you apply a chain rule of like the x over the 2x times on that end of it?
On this side.
Right.
See, I don't see any chain rule here. First of all, when I went to write down the e to the 2x, I wasn't doing his derivative. I was just writing him down, so no chain rule on him.
I was saying like if the arc sine with 2x.
Okay, yes. So if and since the arc sine is just of an x, there was no chain rule involved. It was just the rule for arc sine. But of course, yes, if the arc sine had a 2x, then I would, at the end of doing his derivative, would have a little chain rule spit out a 2 from him. Right. Right. So this was just a product rule derivative. It did involve this new arc sine derivative rule we should have memorized, along with a lot of other stuff we're trying to memorize. You know, I'm finished. If there's not a lot of cleaning here. You could factor out the e to the 2x if you felt like it. You could work on getting a common denominator. I don't in these situations. I'm happy with that. What else? Yes, ma'am.
I had a question on 21 on 3.6.
In 3.6, she's asking about 21. That's a nice question. In 3.6, 21 is a function. It's an x times an arctangent of x. And I haven't even read the question yet, but if I'm thinking about this derivative, what are y'all thinking? Product rule again? That's a little product rule again. Yes, it is. What is the question? Oh, wait. Whoa. It's even more than that. I'm sorry about that. I didn't even read that good at all. Did not read that well at all. It's x, arctangent of x, equals e to the y. Sorry about that. X, arctangent of x, equals e to the y. Wow. Again, if you are going to do a derivative, you still would say to yourself product rule, but you would also say something else to yourself. What else would you say to yourself? Implicit. Yeah, this is an implicit situation. I can try to do an implicit derivative here, I guess. What do they want? Find dy dx at the given point. Okay, so they did give me a point. 1, ln of pi over 4. So they want the derivative at that point. All right. It's a pretty good question. I would do a nice implicit derivative. You ready? An implicit derivative means you just walk in on the left side and start doing derivatives. Knock them all out, right across the equal sign and everything. Just do everybody's derivative. When you see x's, you just do those derivatives normally. When you run into a y, you kind of do that derivative normally, except you tack on a little dy dx. We've tried to explain that as a kind of a chain rule phenomenon there, but here we go. On this side, a product rule. Here we go. Derivative of x.
1.
Very good. And then write down the arctangent of x. And then plus, write down the x. And now, take the derivative of arctangent x. Again, I got it memorized. Do you guys have it memorized?
U prime over 1 plus u squared.
Yes. And did you hear what he said? He called it u prime over 1 plus u squared. And if that x was more than just an x, we would call it a u and sort of follow his directions. With x just being an x there, it's just 1 plus x squared, and the chain rule, you don't really do a chain rule, do you? If you wanted to do a chain rule, what would it spit out? A 1. That's your u prime there. It's just a 1. Okay, cool. We did a product rule. Equals, how do you do the derivative of this other side? The derivative of e to the y is e to the y times dy dx. They want dy dx. If they didn't give me a point and they wanted dy dx, what would I do? If they didn't give me a point, I'm almost done, what would I do? Divide by e to the y, and I'd have dy dx. It would be this big mess over e to the y, right? All right, I don't really want to do that. Because they gave me a point, I think I want to just plug in my point as soon as I can. X is a 1, and y is the ln of pi over 4. So I'm going to plug in my point real quick. I'm going to have the arctangent of 1 right here. I know what that is, but your calculator could help you. This is a 1. This is 1 over 1 plus 1. And what am I plugging in for y? The ln of pi over 4. And all this stuff turns into some nice numbers here, to tell you the truth. Do you know? Yes, Carlos?
So when we have a point like this right here, you don't point the limit until you can't simplify any further. And why is it that you can't go any further from the second line?
So they wanted me to find the derivative, which I'm about to find. They wanted me to find it at this point. So when I got the derivative kind of done, I felt like I could plug in this point. I plugged in the point, and I'm going to work on cleaning it up here. I think it's easier. There's other ways to do this problem. There's never one way to do stuff usually. There's a lot of ways to do stuff. But one way to do it is go ahead and plug in that point like I did. I'm going to clean this up. You guys know the arctangent of 1? It's pi over 4, 45 degrees. You should know that. It's the angle whose tangent is 1. It's the most famous angle whose tangent is 1. Your calculator would help you. Put your calculator in degree mode, find the arctangent of 1, and it'll say 45 degrees. The problem is we don't use degrees, we need pi over 4. This is a 1/2. What's wrong, Carlos? What?
So the wait until you have dy over dx visible before plugging that point, or
Yeah, I needed the derivative. Yeah.
so wait till dy over dx, is in place, and then that's when you plug the point.
Yes.
Yep.
Good. Hey, what about this side? E and log cancel, of course. It's pretty easy. You get a pi over 4 times dy dx, right, you guys? That's what's kind of nice of them, that e and log cancels right there. All right, I'm going to solve for dy dx. I got one more move. What would you do?
Divide by pi over 4.
Divide by pi over 4. You know what I would do? I would multiply by 4 over pi.
Oh.
It's the same thing, right? So that's what I'm doing. I'm multiplying by 4 over pi. It cancels on this side, and here we go. Here we go. If you multiply this by 4 over pi, this is your answer. This is some number. This is my answer. And I could play around a little longer and make it look cleaner or nicer. But this is the derivative at this point. It was an implicit derivative. We evaluated it at this point. We had to know some stuff. We had to know the arctangent of 1. We had to know how to cancel an e and a log. I am going to distribute that through. What's kind of fun here is when it distributes through, that first term becomes a 1, and the next term becomes a 2 over pi. So this is a different looking answer. Sure does look different, but it's the same answer when you distribute that through. Some people would get a common denominator right here. Here's another looking answer. Pi plus 2 all over pi. Some people would say, hell with that. Give me my calculator. I'm going to decimalize it. And you can decimalize it, and you would get some decimal approximation here. What is that decimal approximation? Pi plus 2 divided by pi. Yeah, thank you. 1.64 perhaps, if I round it there. What does that number mean?
That's the derivative of the line at that specific point.
Yeah, so what is that? I didn't really, she said derivative, but I'm thinking of a different word. What is this number? Thank you, the slope. It's the slope of my tangent line. I mean, that's what derivative is, but I'm just trying to see if you remember that. After a full chapter of doing derivatives, you might forget what the hell it really means. Thank you. This is the slope of the tangent line. This is some crazy implicit relationship here. But at that point, the slope is that number. Right. Yes, Carlos?
Right there in the first answer, are you sure that you'd be happy with that? Because it looks like it can obviously be, somebody even further, like, what you have over there for the ones next to him. So, would you mark any points down if, the first answer did an answer like that in the exam?
No. Any other good questions anywhere? You want to work on anything else? Anything on the take-home quiz? Oh, I had one I wanted to do. Here, I'm sorry. I want to do one. I'm in 3.6. I'd like to do this 73. 73 is another little word problem I like. Let's talk about this. 73 in 3.6. It says there's an airplane that's flying overhead. It's got a good picture of this for me. There's an airplane up here. It's so far above the ground. Did they say how far above the ground it was?
5 miles.
5 miles above the ground. That's cool. That's about 25,000 feet or 26,000 feet, I guess. And then I'm just a person down here observing this airplane. I'm looking at this airplane. there's an angle of elevation from me to the airplane. There's an angle of elevation from me to the airplane. Now this airplane is flying towards me though, so what's going to happen to this angle of elevation? I think so, don't you think? I'm watching this airplane come at me. I think the angle of elevation is going to grow. Don't you agree? So, what is changing in this problem? I think this distance is changing. I think that the airplane's coming towards me. I think this distance is changing. I think this angle is changing in this problem. Do you agree? What's not changing is the 5 miles. It's just 5 miles. The airplane's not changing height. Thank goodness. So, I think I got a couple of variables and a constant here, and I've got a situation described for me well. They got a good picture here. What is the question? The question says, write theta as a function of x. They want me to write theta as a function of x. I think you would use trigonometry. And what's your first thought? What would you write down? Just what's a good first thought? You may not have the right answer, but your first thought is, yeah, I think I hear something. You got an angle, you got an opposite side, you got an adjacent side. Tangent pops into my brain. And in fact, I think I'll just write some trig here. The tangent of theta is 5 over x, opposite over adjacent. Now, this is beautiful. This is the relationship between theta and x. But what they wanted was theta written as a function of x. So that means they want theta by itself. They want theta written as a function of x. So how do you get theta written by itself? There's a couple ways to say it. You could just rewrite this as theta is the arctangent of that number. If the tangent of this angle is that number, then the angle is the arctangent of that number. Another way to approach it is let's do the tangent inverse of both sides. The tangent inverse will kill the tangent. That's a good way to say it, to help you get theta by itself. So theta is the tangent inverse of 5 over x. Listen, one more time. I hope you shouldn't be confused. I use these words are interchangeable, right? Tangent inverse or arctangent. And I can say either one and I can write either one. They're the same, right? Arctangent or tangent inverse. But anyway, I just answered part A. Find the tangent inverse, or find theta as a function of x. Part B probably wants me to do a derivative. Probably. What is it? Let's see what it says. The speed of the plane is 400 miles per hour. That's interesting. And then they want me to find d theta dt when x is 10 and when x is 3. They want me to find d theta dt. Yes, Carlos?
Over there where you have 10 theta equals 5 over x, I see how you got that. But where you have 10 inverse, how did that come about?
Well, you could say I took the tangent inverse of both sides. The tangent inverse of tangent cancels it, leaves me theta. And then the tangent inverse of this side is this.
But how does tangent inverse cancel with a theta right there?
Well, tangent inverse cancels tangent because they're inverses of each other. They're inverse functions of each other.
Isn't that 1 over tangent?
No, it's not 1 over tangent. It's the tangent inverse function. It undoes a tangent function. It's the inverse of it.
Oh, I definitely better write that down.
Hey, this is interesting. They're telling me to take the derivative of theta with respect to t. They almost, I think they're a little early. I mean, we learned about this up in 3.7. In 3.7, we learned about these related rates. And we learned how we would probably have an equation where we took the derivative where there's no t's in the equation, but we take the derivative with respect to t. We worked on that Friday. We haven't worked on it today. here I am in 3/6, and I kind of thought they just wanted me to take the derivative with respect to x, but they said, let's take the derivative with respect to t. That's what they said. So I sort of need a little bit of Friday's knowledge to do this. I mean, what it is I just walk into every variable and take the derivative with respect to t. So I walk into to theta, the derivative with respect to t. Let's do this guy. How do you do the derivative of tangent inverse? 1 over 1 plus that stuff squared times the derivative of that stuff. Let's go over here to the scrap paper a second. How do I do the derivative of a 5 over x? How do I do that derivative? Oh, yeah, I don't really do a quotient rule, although it would work. I don't do a quotient rule. I just move the power. It's just a power rule, but you got to move it up and do a power rule. You got to make it 5x to the negative 1, and then when you do the derivative, it's negative 5x to the negative 2. That's the derivative. Negative 5 over x squared, you could say. And now I'm done. I'm done with the chain rule, except I am trying to do this derivative with respect to t. So what do I do at the end here? I just took the derivative of a bunch of x's, so at the end, I think I need dx dt. Yeah. Yep. I mean, this is almost a related rate problem. This is actually kind of from 3/7, because you're taking this derivative with respect to t. This is a relationship with no t's in here, but we took the derivative with respect to t. On one side, it's easy, d theta dt. Hang on, let me just remind you of something. Friday, we had this discussion about a circle that's growing. And if I want to know how fast the area is growing, I would take this derivative with respect to t. This was related rates from Friday, and I would take the derivative of him with respect to t. Then I'd walk over here and I'd do this derivative. How would you do this derivative? The r is the variable. The pi is a number. Bring the 2 down. 2 pi r to the first. Right, you guys? And then I'm done with the derivative, except if I'm doing it with respect to t, I better tack on a little dr dt at the end of this. And what I have is the rate of change of the radius related to the rate of change of the area. I have these related rates. Anyway, that's what this problem was, really. That's what this problem was. Hey, let's finish the details of this problem. This is pretty good. I mean, you know, you guys, this was easy. Rewriting this was kind of easy. Doing this derivative took a little work. You see this chain rule action at the end took a little work. But now, this is a word problem. There's some numbers we can fill in here, I think. They said, let's find this rate of change when x is 10. So let's find d theta dt when x is 10. Yes, Carlos? I think I want to finish this problem, but what do you want to say?
Oh, it's a quick question. Over there, part B, I started to lose it midway. What did you do over there where you had negative 5 over x squared and then multiplied by dx over dt?
Right. Well, I took the derivative of, I went over here and showed you how to do the chain rule. First, I did the derivative of tangent inverse, and then I did the derivative of this. I did his derivative, which is this. Over here. I did the derivative of that 5 over x. There it is.
What about the dx over dt?
Yeah, I'm doing this derivative with respect to t. So I have, at the end of this, I have to take the derivative of that little x with respect to t.
But isn't x supposed to be theta?
No.
It says dt, I mean d theta over dt.
Mm-hmm.
dx over dt. What's the reason that you multiply by dx over dt right there?
I'm taking the derivative of this equation with respect to t. So when I run into this variable, I have to do the derivative with respect to t. And when I do this derivative work, at the end, I have to do the derivative of this variable with respect to t. I have to do the derivative of every variable with respect to t. All right. Hey, when x is 10, I should be able to fill all this in and get an answer. Let's see what happens. d theta dt, x is 10. Does that mean 10 miles, by the way? Yeah, x is 10 miles. Okay, x is in miles. Here we go. 1 plus 1, I'm plugging in a 10 right there. 5 over 10 is 1/2 squared. What am I doing? I'm plugging in a 10 right here. 10 squared is 100. Now, what about this? What the heck is this? Well, I didn't read the problem completely for you, and maybe you didn't read it. Listen to this. The speed of the plane is 400 miles per hour. That's key. The speed of the plane, this guy's coming at me at 400 miles per hour. Can you tell it? That sounds like a rate of change to me. Who do you think's changing? If he's heading this way, who do you think is changing? Who's changing? When he gets over here, I think x is changing. I think that's dx dt. Don't you think? I think that's the rate of change of x. The plane is flying at me, and this distance x is changing. That's dx dt. That was given in the problem as the speed of the plane. It's the rate of change of this variable x, which is this distance, with respect to time. And you know what? Is this x distance growing or decreasing? Is this distance increasing or decreasing?
Decreasing.
It's decreasing, therefore I think I better call that rate of change negative 400 miles an hour. So this dx dt is negative 400 miles per hour. Everything's in miles, so this is good. Everything's in miles. So I won't change it. It's in hours. It's going to be miles and hours, I guess. All right. I got all the numbers in there. Now it's just a matter of figuring out what this is. Let's see what this is. Boy, oh boy, oh boy. Let's see. I can cancel that. That'll be a 4. That'll be a 20. That's a 20 over a 1 plus 1/4 or 5/4. Let's see. That's 20 over 5/4. You can flip it up and multiply by 4/5. You know what this is? 16. d theta dt is 16. d theta dt is 16. All right, hold on. You can't leave until you figure out the units. 16 what? What? What are the units? Degrees? It's an angle, so she said degrees. Sorry, but there's no degrees in this problem. What else could it be if it's not degrees?
Is the angle of elevation?
Theta is an angle. Angles are measured in degrees or radians. If there ain't no little degree thing, it's radians. Over time. And what's our time? It is hours. That's because of that. So you're right. So it's 16 radians per hour. That's the rate of change. Which makes no sense to me.
No, it doesn't.
I mean, it's okay, but let's convert it. Let's convert it. This is difficult for students. I'm going to try to help you do this. That's why I'm making you do this. Let's convert it to degrees per second instead of radians per hour. Let's convert it. Do you know how to convert radians into degrees? What do? I multiply by
180 over 5.
Oh, 180 degrees is the same as pi radians. So now I'll be canceling my radians. I'll be in degrees. Yeah. If I multiply by 180 over pi. You're right. How do I get out of hours? Hours. 1 hour is the same as 60 minutes. 60 minutes is the same as, minutes. 1 minute is 60 seconds. In other words, 1 hour is 3,600 seconds. This is converting. It's kind of cool to be good at converting. This will make more sense, and now this will be degrees per second. This is a better answer, I think. Help me out. 16 times 180 divided by pi, also divided by 3,600. Oh yeah, good old 0.25 degrees every second. Is that what y'all got? That makes a little more sense. Remember, look at me. I'm watching this airplane. How's this angle changing? 0.25 degrees every second. By the way, though, that's only at this instant, which was what instant? Hang on, what instant was this? Oh, when the plane was 10 miles away. When it gets closer to me, I think that rate of change might speed up. In fact, right when he flies over my head, I might get whiplash. Right? This rate of change of the angle, I think, changes. But here it is at the instant when x is 10. Listen, we're going to have to quit today. I got some quizzes to hand back to you.